The universe begins as a furnace of pure energy, where light cannot travel more than a breath's distance before striking another particle. For 380,000 years, a duration that spans the entire history of human civilization repeated hundreds of times, photons ricochet endlessly through a fog of plasma so dense that transparency remains as impossible as sight through molten steel. The cosmos exists as an opaque ember, glowing at temperatures of 3000 Kelvin, hot enough to vaporize any solid matter instantly, yet cool enough that the dance between matter and energy begins to shift toward matter's favor. Within this seemingly chaotic soup, hydrogen and helium nuclei drift like seeds waiting for their season to arrive. These nuclei, forged in the first 3 minutes after the Big Bang, carry within their simple structures the blueprints for every atom that will ever exist. Hydrogen nuclei, single protons born from the decay of neutrons, outnumber helium by 12 to 1, establishing a ratio that will persist throughout cosmic history. Yet even these fundamental particles remain prisoners of the plasma's intensity, unable to capture the electrons that will complete their atomic architecture. The temperature drops with mathematical precision as space expands, following a relationship so exact that cosmologists can calculate the universe's thermal history to fractions of degrees across billions of years. Each doubling of the universe's size cuts the ambient heat in half, obeying laws that will govern every cooling coffee cup and dying star for the next 13 billion years. The expansion proceeds not as an explosion into existing space, but as the creation of space itself, every point moving away from every other point in a choreography that has no center and no edge. The plasma cools through stages that mirror the reverse of stellar fusion, each temperature threshold unlocking new possibilities for matter's organization. At 4000 Kelvin, electrons begin to linger near nuclei for microseconds before thermal agitation tears them away. At 3500 Kelvin, the first fleeting bonds form and dissolve in quantum flickering. The universe hovers at the edge of transformation, like water approaching its freezing point, where the slightest change in conditions will restructure everything. The cooling continues with relentless patience. Space expands at rates measured in kilometers per second per megaparsec, a velocity that seems impossibly slow on human scales yet drives the universe's most fundamental transformation. As the temperature drops through 3200 Kelvin, then 3100, the balance between ionization and recombination shifts imperceptibly. Free electrons, which have spent 380,000 years as prisoners of thermal chaos, begin to sense the gravitational whispers of nearby nuclei. When the universe finally cools below the critical threshold of 3000 Kelvin, something extraordinary occurs with the quietness of dawn breaking over a still landscape. Electrons settle into stable orbits around hydrogen and helium nuclei, neutralizing their electric charges through a process so gentle it releases energy as the softest possible light. The plasma state, where matter exists as a sea of separated charges, gives way to neutral atoms in a transition astronomers call recombination. Though these electrons and nuclei have never been combined before, without free electrons to scatter them, photons suddenly find themselves liberated to travel unimpeded across expanding space. The cosmic fog lifts like morning mist dissipating from a valley, revealing for the first time the universe's own vastness to itself. Light that has been trapped in an endless pinball game of scattering suddenly streams freely across distances that grow larger with each passing moment. The universe becomes transparent to its own light in a transformation as profound as the opening of eyes. This moment of first transparency creates what astronomers detect as the cosmic microwave background, the afterglow of creation that still bathes every cubic centimetre of space with the faintest possible warmth. The light that emerges carries within its wavelengths the imprint of density fluctuations that existed when the universe was barely 0.003% of its current age. These tiny variations in temperature, measured in millionths of degrees, preserve the fingerprints of quantum fluctuations that will later grow into galaxy clusters spanning hundreds of millions of light years. Like a photograph taken when the universe first learned to see, these photons begin a journey that will last longer than the formation of solar systems. They stream outward through space that continues expanding around them, stretching their wavelengths from visible light toward the infrared, then into radio frequencies that will eventually require the most sensitive instruments ever built to detect. The universe's first clear vision of itself embarks on a voyage toward observers who will not exist for billions of years. The irony settles quietly across 13 billion years of cosmic evolution. The very transparency that allows light to escape also creates the darkness that follows. With no more free electrons to maintain the plasma's glow, and no stars yet born to generate new light, the universe enters what astronomers call the Dark Ages, not because light ceases to exist, but because no new sources have yet learned to shine. The first stars lie hundreds of millions of years in the future, waiting for gravity to gather enough neutral hydrogen into the dense cores that will ignite nuclear fusion. Yet even in this darkness, structure begins to emerge with the persistence of rivers carving canyons. Dark matter, which comprises 5 times more mass than ordinary matter but interacts only through gravity, continues its slow work of cosmic scaffolding. These invisible particles, immune to electromagnetic forces, create the framework upon which all future architecture will rest, like foundation posts driven deep into cosmic bedrock. Dark matter concentrates into vast filaments and nodes that will guide the formation of the first galaxies. The universe has gained the gift of sight only to discover that most of its construction occurs in shadows too deep for light to penetrate. This first lesson in cosmic humility, that visibility reveals only a fraction of reality, will echo through every future astronomical discovery. What can be seen depends entirely on what chooses to shine, and most of the universe's matter prefers the anonymity of darkness. In the expanding darkness between these invisible scaffolds, newly formed hydrogen atoms drift with currents of space itself. Each atom carries no electric charge, emits no visible light except for the occasional quantum whisper of the 21-centimetre line, and interacts only through gravitational whispers too faint to measure without instruments more sensitive than the atoms themselves. Yet these simple structures, each containing a single proton embraced by a single electron in the most fundamental of all chemical bonds, hold within their nuclei the fuel that will power every star that ever burns. The cosmic microwave background photons continue their journey outward, carrying the universe's baby pictures toward a future filled with possibilities that exist only as quantum potential. When human telescopes finally detect this ancient light in 1965, they will find it stretched by 13 billion years of expansion into radio wavelengths, cooled to just 2.7 degrees above absolute zero. The universe's first clear vision of itself will arrive precisely when intelligence evolves the tools to receive it, a coincidence that spans the entire history of time, suggesting either extraordinary luck or patterns too deep for current understanding to fathom. The mystery deepens in its mathematical precision. The same physical constants that allow atoms to form also determine the wavelengths at which this ancient light can be detected. The same expansion that cools the universe below the threshold for plasma also stretches primordial photons into frequencies that terrestrial radio telescopes can capture. The universe seems to have arranged its own observation, timing the arrival of its earliest signals to coincide with the emergence of observers capable of recognizing their significance. In the darkness that follows the universe's first dawn of transparency, gravity begins its patient work of architecture. Dark matter, invisible to the photons now streaming freely through space, responds only to the subtlest of forces, the gentle pull that operates across distances measured in millions of light years. These particles, 5 times more abundant than the ordinary matter that will eventually form stars and planets, drift through the expanding cosmos like seeds of structure waiting for the right conditions to take root. The dark matter does not distribute itself evenly across space. Quantum fluctuations from the universe's earliest moments have left microscopic variations in density, regions where matter clusters slightly more densely than the cosmic average, separated by voids where particles spread more thinly. These differences, invisible to any possible observer at the time, amount to variations of only 1 part in 100,000. Yet across the vast scales of cosmic expansion, even such tiny irregularities become the foundation stones of everything that will follow. Gravity amplifies these whispers of variation with the patience of geological processes stretched across cosmic time, where dark matter concentrates even slightly. Its gravitational influence draws in more particles from the surrounding regions. The rich grow richer in a process that unfolds over millions of years, each generation of clustering creating slightly denser cores that attract matter from ever wider regions of space. Like water flowing toward the lowest points in a landscape, dark matter begins to pool in invisible valleys carved by its own gravity. The process accelerates with mathematical inevitability. Regions that start only 0.001% denser than average grow to twice the background density, then 10 times, then 100-fold. The universe's smooth beginnings give way to a cosmic web of filaments and nodes, vast structures that span hundreds of millions of light years, yet remain completely invisible to any form of electromagnetic radiation. Dark matter constructs the universe's skeleton while ordinary matter drifts unknowingly through this invisible scaffolding. The hydrogen and helium atoms, newly freed from their plasma prison, follow gravity's invitation with reluctant obedience. These ordinary matter particles, unlike their dark cousins, can lose energy through radiation. Electrons dropping between energy levels emit photons that carry heat away into the expanding void. This ability to cool allows ordinary matter to condense more efficiently than dark matter, falling toward the centers of the gravitational wells that dark matter has excavated across cosmic space. Yet the hydrogen resist compression with quantum stubbornness. Each atom occupies a precise volume determined by the electromagnetic force that binds electron to proton, creating a natural resistance to the gravitational pull that seeks to draw atoms together. The balance between these forces, gravity pulling inward, quantum pressure pushing outward, determines how much ordinary matter can accumulate before other processes intervene. For now, hydrogen clouds grow denser but remain far too diffuse to ignite the nuclear fires that await in stellar cores. The first protogalactic clouds begin to take shape in regions where dark matter has excavated the deepest gravitational wells. These structures, still invisible to any form of observation, span distances comparable to modern galaxies, yet contain matter so thinly distributed that entire solar systems could fit within the spaces between individual atoms. The universe constructs its largest structures from components so sparse they approach the vacuum of intergalactic space, a paradox that will perplex cosmologists for decades after they finally detect these ancient formations. Temperature variations within these early clouds follow patterns that mirror the quantum fluctuations from which they emerged. Regions that collapse fastest heat up through gravitational compression, while areas that remain more diffuse cool through radiative losses into the cosmic background. These temperature differences, measured in fractions of degrees, create pressure gradients that drive the first atmospheric currents in cosmic history. Vast rivers of hydrogen flowing through gravitational valleys toward destinations that will not form for hundreds of millions of years. The mystery of dark matter's composition deepens as its influence becomes more apparent. Whatever particles constitute this invisible majority, they interact with ordinary matter only through gravity, passing through hydrogen and helium atoms as if they occupied completely separate universes. Yet their gravitational signatures carve the pathways that ordinary matter will follow, creating a hidden geography that determines where the first stars will eventually ignite. The universe builds its visible structures on an invisible foundation, whose nature remains unknown even to observers 13 billion years in the future. The irony of cosmic construction reveals itself in the mathematics of structure formation. The very expansion that dilutes matter also provides the time necessary for gravity to overcome the initial smoothness of the early universe. Had expansion proceeded faster, gravitational clustering would never overcome the dispersive effects of cosmic stretching. Had it proceeded slower, the universe would have collapsed back into itself before the first structures could form. The rate of expansion maintains a precise balance that allows complexity to emerge from simplicity through gravitational amplification of quantum noise. Dark matter filaments grow like neural networks across the expanding cosmos, connecting nodes of higher density through bridges of slightly concentrated particles. These cosmic highways will eventually guide ordinary matter along preferred routes toward the regions where galaxy formation becomes most efficient. The universe develops its own transportation infrastructure, built from invisible materials according to blueprints written in the language of quantum fluctuations and gravitational mathematics. The process unfolds with the steady rhythm of physical law applied across cosmic scales. Each passing million years sees the contrast between dense and sparse regions grow more pronounced. The gravitational wells deepen. The flows of matter along dark matter, filaments accelerate toward their eventual destinations. The universe constructs its architecture without architects, following algorithmic rules that produce structures of breathtaking complexity from the simplest possible initial conditions. In the deepest gravitational wells, where dark matter has concentrated most efficiently, ordinary matter begins to approach densities that hint at future possibilities. Hydrogen clouds in these regions reach concentrations thousands of times greater than the cosmic average, yet still remain more diffuse than the best laboratory vacuums. These barely perceptible concentrations mark the locations where the first stars will eventually ignite. Though the nuclear furnaces that will illuminate the cosmic dark ages still await the accumulation of vastly more material through gravitational collapse spanning hundreds of millions of additional years, in the heart of the deepest gravitational wells, where dark matter has carved the most profound valleys in spacetime's geometry, hydrogen begins its slow surrender to the inevitable pull of nuclear destiny. The first protostars emerge, not as sudden ignitions, but as gradual concentrations of matter that cross invisible thresholds with the patience of mountains rising from tectonic pressures. These stellar nurseries form in regions where the cosmic web's filaments intersect, creating nodes of enhanced density that will become the birthplaces of the universe's first suns. The hydrogen clouds that collapse toward these gravitational centers carry within their simple atomic structure a cosmic inheritance spanning back to the first 3 minutes after the Big Bang. Each proton remembers its birth in the primordial nuclear synthesis, when the universe was hot and dense enough to forge the lightest elements from pure energy. Now, hundreds of millions of years later, these same protons drift toward reunions that will release the energy stored in their nuclear binding, transforming gravitational potential into the light that will end the cosmic dark ages. The collapse proceeds through stages that mirror the formation of planetary systems, yet on scales that dwarf the architecture of solar formation. Initial hydrogen concentrations span light years in diameter while containing masses equivalent to millions of future suns. As gravity draws this material inward, conservation of angular momentum accelerates rotation rates, flattening the collapsing cloud into disks that rotate with periods measured in millions of years. The universe's first stellar nurseries spin like vast, lazy pinwheels composed of hydrogen so pure that not a single atom heavier than lithium contaminates their primordial composition. Within these rotating disks, turbulence creates smaller eddies and condensations, each following fractal patterns that repeat across multiple scales of size and mass. Regions of slightly higher density within the larger cloud begin their own subsidiary collapse. Creating a hierarchy of structures within structures, the universe demonstrates its preference for complexity emerging from simplicity. As single large clouds fragment into clusters, then into individual stellar cocoons, each destined to become a nuclear furnace burning with temperatures that recreate conditions from the universe's earliest moments. The first stars to achieve nuclear ignition differ fundamentally from every star that will follow them in cosmic history. These population 3 stars, as astronomers will eventually classify them, form from hydrogen and helium so pure that they lack even trace amounts of heavier elements. Without metals to facilitate cooling through radiative losses, these primordial clouds must collapse to much higher densities and temperatures before they can shed enough heat to continue contracting. The result produces stellar monsters with masses hundreds of times greater than the Sun that will eventually illuminate Earth's skies. The journey from first gravitational stirring to nuclear ignition spans tens of millions of years, a duration that seems brief only when measured against cosmic timescales, yet represents periods longer than entire species will later exist on terrestrial worlds. Throughout this lengthy gestation, the collapsing hydrogen experiences pressures and temperatures that gradually approach the thresholds necessary for nuclear fusion. At 10 million Kelvin, protons begin to overcome their electromagnetic repulsion through quantum tunneling, allowing the strong nuclear force to bind them into helium nuclei with the release of energy that has waited since the universe's creation to escape. The first stellar ignition occurs with the gentleness of sunrise spreading across a landscape, yet generates energy outputs that will eventually be detectable across billions of light years. Nuclear fusion begins in the dense core where temperatures and pressures reach the critical thresholds, then gradually spreads outward as the released energy heats surrounding hydrogen to fusion temperatures. The star establishes hydrostatic equilibrium, gravity pulling inward balanced by radiation pressure pushing outward, creating a stable configuration that can burn for millions of years before exhausting its nuclear fuel. These earliest stars burn with extraordinary brilliance, converting hydrogen to helium at rates thousands of times faster than later. Metal-enriched stars will manage. Their surface temperatures reach 50,000 Kelvin, making them appear blue-white to any hypothetical observers. Though no planets yet exist to provide viewing platforms for such spectacular displays, the universe's first artificial suns illuminate regions of space spanning hundreds of light years, their radiation ionizing the neutral hydrogen in surrounding regions and creating the first bubbles of hot plasma since the cosmic microwave background emerged from recombination. The stellar winds from these massive stars carry energy and momentum far into the surrounding interstellar medium, pushing against the neutral hydrogen with pressures that create shock waves traveling at thousands of kilometers per second. These stellar hurricanes carve cavities in the cosmic web's filamentary structure, creating the first organized regions of hot, ionized gas since the universe cooled below plasma temperatures. The interstellar medium begins its transformation from pristine neutrality toward the complex ecology of hot and cold phases that will characterize galaxy formation throughout cosmic history. Nuclear fusion in stellar cores operates through the proton-proton chain, the same sequence of reactions that will power the Sun billions of years in the future, yet with efficiencies enhanced by the extreme conditions within these massive primordial stars. 4 hydrogen nuclei combine through a series of intermediate steps to produce one helium nucleus, 2 positrons, 2 neutrinos, and 26.7 million electron volts of binding energy. This energy, released in the form of gamma-ray photons, begins a random walk toward the stellar surface that will require thousands of years to complete. As each photon scatters countless times through the dense stellar interior, the helium produced by hydrogen fusion accumulates in stellar cores with the inevitability of ash gathering in a fireplace. Yet this nuclear ash carries within its structure the potential for even more energetic fusion reactions. When core temperatures rise above 100 million Kelvin, helium nuclei begin fusing into carbon through the triple alpha process, a reaction so improbable that it requires the simultaneous collision of 3 helium nuclei, yet becomes inevitable given stellar lifetimes measured in millions of years. The universe begins its slow construction of the periodic table, element by element, through successive generations of nuclear burning. The mystery of stellar nuclear synthesis lies not in the fusion reactions themselves, which follow well-understood principles of nuclear physics, but in the precise conditions that allow these reactions to proceed at sustainable rates. The temperature and pressure requirements for nuclear fusion exist within extremely narrow ranges, too cool, and protons lack sufficient energy to overcome electromagnetic repulsion, too hot, and the resulting radiation pressure would blow the star apart before sustained fusion could establish itself. The universe's first stars navigate these constraints with the precision of tightrope walkers, maintaining nuclear burning rates that release energy at exactly the pace required for stellar stability. The irony of population 3 stellar evolution reveals itself in the very conditions that enable their formation. The lack of heavy elements that allows these stars to grow to enormous masses also ensures their rapid consumption of nuclear fuel and relatively brief lifetimes. These stellar giants burn brightly but briefly, exhausting their hydrogen cores in only a few million years before advancing to more exotic fusion processes that will forge elements heavier than carbon. Their massive cores will eventually produce silicon, sulfur, and iron through successive burning phases, each operating at higher temperatures and consuming fuel at accelerating rates. The first generation of stars creates more than just light and heat. They establish the physical and chemical conditions that will enable all subsequent stellar formation. Their intense ultraviolet radiation ionizes hydrogen across vast regions of space, creating temperature and pressure conditions that alter how future generations of stars will form from the interstellar medium. Their stellar winds and eventual supernovae will scatter the first heavy elements across the cosmic web, providing the raw materials from which planets, atmospheres, and eventually life itself will be constructed. Deep within stellar cores, temperatures climb toward the thresholds for silicon burning, the final fusion process that can release energy through nuclear reactions. At 3 billion Kelvin, silicon nuclei begin fusing into iron, the most stable nucleus in the periodic table and the endpoint of energy-releasing fusion reactions. Beyond iron, nuclear binding energy decreases rather than increases, meaning that further fusion would require energy input rather than producing energy output. The universe's first stars race toward this nuclear precipice with accelerating urgency, their massive cores consuming silicon fuel in mere days before reaching the iron catastrophe that will terminate their nuclear lives in explosive violence. The approaching stellar death carries within its inevitability the seeds of cosmic renewal. When these massive stars finally exhaust their nuclear fuel, their cores will collapse in milliseconds, then rebound in core collapse supernovae that release more energy in seconds than the star produced throughout its entire nuclear lifetime. These stellar explosions will scatter the heavy elements forged in stellar cores across vast regions of space, enriching the interstellar medium with carbon, oxygen, silicon, and iron and the essential building blocks of planets and life. Yet for now, in the nuclear hearts of the universe's first stars, fusion proceeds with steady determination through the successive burning stages that will create every element heavier than lithium. Hydrogen converts to helium, helium fuses into carbon, carbon burns to produce neon, neon burning creates magnesium, oxygen burning produces silicon, and silicon burning forges iron. Each stage releases less energy per nuclear reaction and consumes fuel at faster rates, creating a cascade toward the nuclear instability that will end stellar life in the universe's first supernovae. The stellar nurseries that ended the cosmic dark ages prepare for explosions that will illuminate the universe more brilliantly than entire galaxies, while seeding space with the chemical diversity required for the next chapter in cosmic evolution. Within the nuclear furnaces of these stellar giants, the universe begins its methodical construction of complexity, forging elements that will remain stable for billions of years beyond the brief lifetimes of their stellar creators. The massive cores of Population 3 stars operate as cosmic alchemical laboratories, transforming the simplest atomic structures into increasingly sophisticated nuclear architectures through successive burning phases that unfold with the inexorable logic of thermodynamics applied to quantum mechanics. Iron accumulates in stellar cores like snow gathering in mountain valleys, each nucleus representing the endpoint of energy-releasing fusion reactions and the beginning of stellar catastrophe. Unlike the lighter elements produced in earlier burning phases, iron cannot serve as fuel for further fusion reactions that yield net energy output. Instead, iron nuclei require energy input to fuse into heavier elements, creating an insurmountable barrier to continued nuclear burning. The stellar core begins its transformation from energy source to energy sink, setting the stage for gravitational collapse that will dwarf the gentle contraction that first brought these stars to nuclear ignition. The approach toward core collapse proceeds through stages of accelerating nuclear consumption that compress millions of years of stellar evolution into the final centuries of stellar life. Silicon burning, the last energy-producing fusion process, operates at core temperatures exceeding 3 billion Kelvin, conditions so extreme that thermal photons carry enough energy to disintegrate atomic nuclei through photodisintegration reactions. The stellar core becomes a battlefield where fusion attempts to build heavier elements while high-energy radiation simultaneously destroys them, creating a dynamic equilibrium between nuclear construction and destruction. As iron accumulates beyond the critical mass threshold of approximately 1.4 solar masses, a limit that will later be known as the Chandrasekhar mass, electron degeneracy pressure can no longer support the core against gravitational collapse. The stellar interior, which has maintained hydrostatic equilibrium for millions of years through the balance between gravity and radiation pressure, suddenly loses its primary means of mechanical support. Gravity achieves decisive victory over all opposing forces, initiating core collapse that proceeds at velocities approaching a significant fraction of the speed of light. The core collapse unfolds in milliseconds, compressing matter to densities that exceed those found in atomic nuclei and creating conditions more extreme than those that existed during the first microseconds after the Big Bang. Electrons and protons, squeezed beyond their quantum mechanical limits, combine to form neutrons through inverse beta decay, releasing torrents of neutrinos that carry away vast quantities of energy and momentum. The stellar core transforms from a collection of individual atomic nuclei into a single, unified neutron star, a stellar remnant so dense that a teaspoon of its material would outweigh entire mountains on any terrestrial world. The rebounding shockwave from core collapse races outward through the stellar interior at velocities exceeding 30,000 kilometers per second, encountering layers of progressively lighter elements that surround the iron core like nested spherical shells. Silicon, oxygen, neon, carbon, helium, and hydrogen. Each layer records the nuclear history of the star's evolutionary phases, preserved in concentric zones that represent successive epochs of fusion burning. The shockwave processes these layers through explosive nuclear synthesis, creating conditions that forge elements heavier than iron through rapid neutron capture and radioactive decay. These core collapse supernovae become the universe's first factories for producing elements beyond iron, including cobalt, nickel, copper, zinc, and eventually the gold, silver, and platinum that will later adorn terrestrial civilizations. The explosive nuclear synthesis occurs through the rapid neutron capture process, where atomic nuclei absorb neutrons faster than they can undergo radioactive decay, building up neutron-rich isotopes that subsequently decay into stable heavy elements. The universe's first supernovae create more heavy elements in seconds than millions of years of stellar fusion produced through the slower processes of hydrostatic burning. The energy released during these stellar explosions exceeds 10 circumflex 44 joules, more energy than the star produced throughout its entire nuclear lifetime, and sufficient to outshine entire galaxies for months. This energy drives supernova shock waves through the surrounding interstellar medium at velocities that create temperatures and pressures comparable to those found in stellar interiors. The shock-heated gas glows with characteristic spectral lines that will eventually allow distant observers to identify the elements produced in stellar explosions and scattered across cosmic distances through supernova winds. The heavy elements forged in stellar cores and dispersed by supernova explosions begin their journey across the cosmic web, carried by stellar winds and supernova shock waves toward regions where future generations of stars will incorporate them into new stellar compositions. These enriched gas clouds, contaminated with trace amounts of carbon, oxygen, silicon, and iron, will form the raw materials from which smaller, longer-lived stars can eventually emerge. The universe begins its transition from the pure hydrogen and helium of population 3 stars toward the metal-enriched compositions that will characterize all subsequent stellar generations. The dispersal of heavy elements proceeds through multiple physical mechanisms that operate across vastly different timescales and spatial ranges. Stellar winds from massive stars carry nuclear synthesis products into the surrounding interstellar medium throughout their nuclear lifetimes, creating bubbles of enriched gas that expand at velocities of hundreds of kilometers per second. Supernova explosions accelerate this process dramatically, driving shock waves through the interstellar medium that sweep up and mix previously pristine hydrogen with the nuclear ashes of stellar death. The mystery of cosmic chemical evolution lies in the efficiency with which stellar nuclear synthesis products spread through the universe's largest structures. Individual supernova explosions enrich regions spanning hundreds of light years, yet the cosmic web extends across billions of light years. The heavy elements must somehow disperse through galactic and intergalactic distances before they can influence the formation of subsequent stellar generations. This chemical mixing requires mechanisms that operate on scales vastly larger than individual stellar explosions, involving the complex interplay between stellar feedback, galactic dynamics, and the gravitational flows that drive matter along dark matter filaments. Turbulence within the interstellar medium accelerates chemical mixing through processes that mirror atmospheric and oceanic circulation on terrestrial worlds, yet operate across scales that dwarf planetary dimensions. Supernova-driven shockwaves create instabilities in the gas distribution that generate turbulent eddies spanning light-years in diameter. These eddies mix enriched and pristine material through convective motions that gradually homogenize the chemical composition of star-forming regions, ensuring that future stellar generations will form from gas that contains at least trace amounts of heavy elements. The iron forged in stellar cores carries within its nuclear structure a cosmic memory of the extreme conditions that created it. Each iron nucleus required the simultaneous presence of temperatures exceeding 3 billion Kelvin, pressures greater than those found at the centers of planets, and neutron densities approaching those of atomic nuclei. These conditions existed only briefly in cosmic history, during the final moments of massive stellar cores before gravitational collapse terminated nuclear burning forever. Every iron atom in the universe serves as a fossil record of stellar death, preserving evidence of nuclear processes that operated for mere seconds yet produced elements stable across cosmic time. The irony of stellar nuclear synthesis reveals itself in the relationship between stellar mass and nuclear legacy. The most massive population 3 stars burn through their nuclear fuel most rapidly, achieving the highest core temperatures and producing the greatest diversity of heavy elements, yet live the shortest lives before exploding as supernovae. Their nuclear products scatter across vast regions of space, enriching the interstellar medium for future generations while eliminating the stellar furnaces that created them. The universe's first heavy element factories destroy themselves in the very process that creates their most important products. These stellar explosions illuminate the cosmic web with light visible across billions of light years, creating transient beacons that outshine their host galaxies while scattering nuclear ashes into the intergalactic medium. The supernova light curves follow predictable patterns determined by the radioactive decay of nickel-56 into cobalt-56, and eventually into stable iron-56, creating a cosmic clock that measures the expansion of supernova ejecta. The universe's first supernovae established the template for stellar death that will repeat throughout cosmic history, each explosion adding incrementally to the growing inventory of heavy elements available for planet formation. The carbon, oxygen, silicon, and iron dispersed by these explosions will eventually find their way into the atmospheres of rocky planets, the cores of terrestrial worlds, and the biochemical structures that enable life itself. Yet, for now, in the immediate aftermath of the universe's first stellar deaths, these heavy elements exist as trace contaminants in vast clouds of hydrogen and helium, their concentrations measured in parts per million relative to the dominant light elements. The chemical diversity that will eventually enable planetary formation and biological evolution begins as the faintest possible seasoning in an overwhelmingly simple cosmic soup. The supernova shockwaves race outward from their stellar birthplaces like expanding spheres of nuclear revelation, carrying within their turbulent fronts the scattered ashes of stellar death across distances that will eventually span entire galactic halos. These blast waves, traveling at velocities exceeding 10,000 kilometers per second, sweep through the pristine hydrogen and helium of the early universe with the transformative power of cosmic hurricanes, mixing heavy elements into regions that have remained chemically unchanged since the first moments of nucleosynthesis 3 billion years earlier. The dispersal unfolds through phases that mirror the atmospheric dynamics of planetary weather systems, yet operate across scales that dwarf the orbits of entire solar systems. Initial supernova explosions create hot bubbles of enriched plasma that expand into the surrounding interstellar medium. Like cosmic soap bubbles blown from stellar cores, these superbubbles grow to diameters spanning hundreds of light years, while maintaining internal temperatures of millions of degrees, creating vast cavities in the cosmic web, where heavy elements mix with primordial gas through turbulent convection that operates for millions of years. Within these expanding shells of enriched material, the heavy elements undergo complex chemical evolution as temperatures and densities change during the ongoing expansion. Iron atoms, forged at billions of degrees in stellar cores, find themselves embedded in cooling plasma where they can capture free electrons and form the first neutral iron atoms in cosmic history. Carbon and oxygen, produced through helium burning in stellar interiors, combine with hydrogen to create the earliest molecular species more complex than the simple diatomic molecules that emerged during recombination. The chemical complexity increases as supernova ejecta cool below the threshold temperatures where molecular bonds can survive thermal disruption. Carbon monoxide forms when carbon and oxygen atoms encounter each other in the expanding debris, creating the first molecular species that will later serve as a crucial coolant in star-forming regions. Water molecules emerge when oxygen encounters the abundant hydrogen of the interstellar medium. Though these early water molecules exist in gaseous form at temperatures far too high for liquid condensation, the cooling supernova remnants create the universe's first dusty environments. As refractory elements like silicon, magnesium, and iron begin to condense into solid grains when temperatures drop below their respective condensation thresholds. These microscopic particles, each containing only a few hundred atoms, represent the universe's first attempt at solid matter formation since the brief epoch when temperatures allowed deuterium nuclei to form in the primordial plasma. The dust grains serve as condensation nuclei where additional atoms can accrete, beginning the slow process of building larger solid structures from individual atomic components. Silicon and oxygen combine to form silicate minerals that mirror the compositions found in terrestrial rocks. Though these cosmic dust grains exist in environments millions of times more tenuous than the hardest laboratory vacuums, magnesium, aluminum, and calcium contribute to complex silicate structures that incorporate multiple elements into crystalline lattices held together by electromagnetic forces. The universe begins its education in solid-state physics, learning to construct materials with properties determined by the arrangement of atoms rather than their individual nuclear characteristics. Iron dust forms through different condensation pathways, creating metallic grains that will eventually serve as the cores of planetary systems and the raw materials for magnetic field generation in rotating worlds. These iron particles, each microscopic yet containing millions of atoms forged in stellar cores, carry within their crystalline structures the magnetic properties that will later enable planetary dynamos and the protective magnetospheres that shield atmospheric evolution from stellar radiation. The dust grains scatter and absorb starlight with efficiencies that depend on their size, composition, and internal structure, creating the first examples of cosmic extinction that will later complicate astronomical observations across all wavelengths of electromagnetic radiation. Submicron silicate particles absorb ultraviolet and blue light preferentially while transmitting longer wavelengths, causing distant stars to appear redder than their true colors. The universe develops its first atmospheric effects, though these occur in the vast spaces between stars rather than within the gravitational boundaries of individual worlds. The growing population of dust grains catalyzes chemical reactions that would otherwise require prohibitively high activation energies in the tenuous conditions of interstellar space. Hydrogen atoms adsorb onto grain surfaces where they can encounter each other with higher probability than in the gas phase, enabling the formation of molecular hydrogen through surface-catalyzed reactions. The dust serves as a cosmic laboratory where chemical complexity can emerge despite the extremely low densities that characterize most of the universe's volume. Molecular hydrogen formation marks a crucial transition in the cosmic chemical inventory, as this simple diatomic molecule becomes the universe's most efficient coolant at the moderate temperatures that characterize star-forming regions. When molecular hydrogen collides with other molecules or atoms, rotational and vibrational excitation followed by radiative de-excitation removes kinetic energy from the gas, allowing gravitational contraction to proceed more efficiently than in regions dominated by atomic hydrogen. The universe learns to build its own refrigeration systems from the chemical products of stellar death. The dispersal of heavy elements creates spatial gradients in chemical composition that will influence star formation for billions of years into the future. Regions close to recent supernovae develop metallicities measured in parts per thousand, while areas far from stellar explosions remain essentially pristine in their primordial hydrogen and helium compositions. These chemical variations introduce heterogeneity into what began as a remarkably uniform universe, creating conditions where different stellar populations can emerge with distinct properties determined by their local chemical environments. The mystery of efficient cosmic mixing reveals itself in the rapidity with which even trace amounts of heavy elements spread through volumes vastly larger than individual supernova remnants. Galactic-scale simulations suggest that turbulent mixing driven by multiple stellar explosions can homogenize chemical compositions across distances spanning thousands of light-years within timescales of tens of millions of years. Yet the physical mechanisms that achieve such efficient mixing remain poorly understood, requiring complex interactions between stellar feedback, magnetic fields, and the gravitational flows that drive matter along dark matter filaments. Stellar winds from surviving massive stars contribute additional heavy elements to the growing inventory of cosmic chemical complexity, though at rates far lower than the explosive dispersal achieved through supernovae. These gentler forms of mass loss operate continuously throughout stellar lifetimes, creating steady streams of enriched material that flow into the surrounding interstellar medium. The combination of explosive and continuous mass loss creates a chemical evolution that proceeds through both catastrophic events and gradual accumulation. The heavy elements carried by supernova shock waves eventually encounter the gravitational wells carved by dark matter concentrations, where they begin to accumulate in the same regions destined to become the sites of future star formation. This chemical enrichment of star-forming regions ensures that subsequent stellar generations will incorporate heavy elements into their compositions from the moment of initial gravitational collapse, fundamentally altering the physics of stellar formation and evolution compared to the pure hydrogen and helium stars of the first generation. The carbon scattered by stellar explosions carries within its nuclear structure the potential for organic chemistry that will eventually enable biological evolution on terrestrial worlds. Each carbon atom, forged through helium burning in stellar cores, possesses the unique ability to form 4 covalent bonds with other atoms, creating the structural flexibility required for complex molecular architectures. The universe distributes the raw materials for biochemistry billions of years before planets exist to host the chemical reactions that will generate life. Oxygen atoms, produced through successive burning phases in massive stellar cores, will eventually enable both the atmospheric chemistry that supports complex life and the oxidation reactions that power biological metabolism. Yet in the immediate aftermath of supernova dispersal, these oxygen atoms exist primarily in highly ionized states, stripped of most electrons by the intense radiation fields that accompany stellar explosions. The universe scatters the components of future atmospheres while they remain too energetic to participate in the gentle chemistry required for molecular complexity. The irony of cosmic chemical evolution emerges in the relationship between stellar death and the emergence of life-supporting conditions. The very explosions that destroy the stellar furnaces responsible for heavy element production also create the dispersal mechanisms necessary to transport these elements to regions where they can participate in planet formation. Stellar death becomes a prerequisite for the chemical complexity that will eventually enable stellar birth in forms sophisticated enough to support planetary systems capable of hosting biological evolution. The expanding supernova remnants begin to interact with each other as the universe's stellar population grows and the frequency of stellar explosions increases across the cosmic web. Overlapping blast waves create complex shock interactions that accelerate the mixing of heavy elements while generating turbulence across multiple spatial scales. The interstellar medium transforms from the pristine simplicity of primordial gas into a dynamic, chemically evolving ecosystem where stellar birth and death drive continuous cycles of enrichment and renewal.